In an electric utility system with almost completely heavy industrial loads, a decent power factor would typically be in the range of 0.85 to 0.95. This range is considered acceptable for heavy industrial loads, which often have a significant inductive component due to the use of motors and other equipment. A power factor close to 1.0 is ideal, as it indicates that the load is drawing real power, kilowatt, without a significant amount of reactive power, kilovolt ampere reactive. Reactive power does not contribute to the actual work being done by the load, but it can cause efficiencies in the transmission and distribution system. Maintaining a decent power factor is important for several reasons. Firstly, reduce transmission losses. Reactive power flowing through transmission lines can cause additional losses due to increased resistance and inductance. A high power factor reduces these losses, resulting in more efficient power delivery. Secondly, improved voltage regulation. Low power factor can lead to voltage fluctuations, which can affect the stability and reliability of the electrical system. Maintaining a decent power factor helps to regulate voltage and prevent voltage instability. Thirdly, reduce power factor penalties. Some utilities impose penalties on customers with low power factors, as it can increase their costs for maintaining the distribution system. A decent power factor can help avoid these penalties. Industrial customers can improve their power factor by using power factor correction devices such as capacitors, synchronous condensers, or static volt-ampere reactive compensators. These devices inject reactive power into the system, offsetting the inductive component of the load and improving the power factor. Power factor is a crucial aspect of electrical systems, particularly in heavy industrial environments where large inductive loads are common. It is defined as the ratio of real power, measured in kilowatts, to apparent power, measured in kilovolt amperes. Real power represents the actual power used by the load to perform work, while apparent power is the vector sum of real power and reactive power. Reactive power, measured in kilovolt amperes reactive, arises from inductive and capacitive components in the circuit. Inductive loads, such as motors, transformers, and reactors, consume reactive power to establish magnetic fields. Capacitive loads, such as capacitors and some electronic devices, generate reactive power. The presence of reactive power in an electrical system can lead to several undesirable effects, including increased current flow, higher transmission losses, voltage drops, and reduced system capacity. A low power factor indicates a significant amount of reactive power, which means that the system is less efficient in delivering power to the load. A power factor close to 1.0, also known as unity power factor, is the ideal scenario. This indicates that the load is drawing only real power and no reactive power, resulting in maximum efficiency. However, in real-world applications, achieving a perfect power factor of 1.0 is often not feasible or cost-effective. Therefore, utilities and industrial facilities typically aim to maintain a power factor within an acceptable range. For heavy industrial loads, a decent power factor is generally considered to be between 0.85 and 0.95. This range strikes a balance between efficiency, costs, and system stability. A power factor below 0.85 may result in significant penalties from the utility company, while a power factor above 0.95 may require excessive investment in power factor correction equipment. Maintaining a decent power factor offers several benefits. Firstly, it reduces transmission losses. Reactive power flowing through transmission lines increases the current flow, which in turn increases the losses due to the resistance of the conductors. By reducing the reactive power, a higher power factor minimizes these losses, resulting in more efficient power delivery. Secondly, it improves voltage regulation. A low power factor can cause voltage drops along the transmission and distribution lines, leading to voltage fluctuations at the load. These voltage fluctuations can affect the performance and lifespan of sensitive equipment. By maintaining a decent power factor, the voltage drop is minimized and the voltage remains more stable. Thirdly, it increases system capacity. Reactive power consumes capacity in the electrical system, reducing the amount of real power that can be delivered. By reducing the reactive power, a higher power factor frees up capacity, allowing the system to serve more loads. Fourthly, it avoids power factor penalties. Many utilities impose penalties on customers with low power factors to discourage excessive reactive power consumption. These penalties are designed to recover the costs associated with maintaining the distribution system. By maintaining a decent power factor, customers can avoid these penalties and reduce their electricity bills. To improve the power factor, industrial customers can employ various power factor correction techniques. One common method is to install capacitors in parallel with the inductive loads. Capacitors generate reactive power, which offsets the reactive power consumed by the inductive loads, thereby improving the power factor. The size of the capacitors must be carefully selected to match the reactive power requirements of the load. Another method is to use synchronous condensers. Synchronous condensers are synchronous motors that are operated without a mechanical load. By varying the excitation current of the motor, the synchronous condenser can generate or absorb reactive power, thereby controlling the power factor of the system. Synchronous condensers are typically used in large industrial facilities with significant reactive power requirements. A third method is to use static volt-ampere reactive compensators. Static volt-ampere reactive compensators are power electronic devices that can rapidly inject or absorb reactive power. They consist of thyristor-controlled reactors and thyristor-switched capacitors, which allow for precise control of the reactive power flow. Static volt-ampere reactive compensators are often used in dynamic applications where the reactive power requirements vary rapidly. The choice of power factor correction method depends on several factors, including the size of the load, the type of load, the load profile, and the cost of the equipment. It is important to conduct a thorough power factor study to determine the optimal solution for a particular application. In addition to installing power factor correction equipment, industrial customers can also improve their power factor by optimizing their operations. This includes minimizing the use of lightly loaded motors, replacing inefficient equipment with more efficient equipment, and reducing the amount of idle time for inductive loads. Regularly monitoring the power factor is also essential to ensure that it remains within the acceptable range. Power factor meters and analyzers can be used to measure the power factor and identify potential problems. If the power factor drops below the desired level, corrective action should be taken promptly. In summary, maintaining a decent power factor is crucial for the efficient and reliable operation of electrical systems in heavy industrial environments. A power factor between 0.85 and 0.95 is generally considered acceptable, but the ideal value may vary depending on the specific application. By implementing power factor correction techniques and optimizing operations, industrial customers can improve their power factor, reduce transmission losses, improve voltage regulation, increase system capacity, and avoid power factor penalties. Power factor correction is not a one-time fix, but an ongoing process that requires regular monitoring and maintenance. As the load profile changes or new equipment is added, the power factor may need to be re-evaluated and adjusted accordingly. Working with a qualified electrical engineer or consultant can help ensure that the power factor is properly managed and optimized. Power factor is also affected by harmonics in the electrical system. Harmonics are sinusoidal voltages and currents with frequencies that are integer multiples of the fundamental frequency. Harmonics can be generated by nonlinear loads such as electronic devices, variable frequency drives, and arc furnaces. Harmonics can distort the voltage and current waveforms, leading to a lower power factor and increased losses. To mitigate the effects of harmonics, harmonic filters can be installed. Harmonic filters are designed to block or reduce the flow of harmonic currents, thereby improving the power factor and reducing losses. There are two main types of harmonic filters: passive filters and active filters. Passive filters consist of inductors and capacitors that are tuned to specific harmonic frequencies. They are relatively simple and inexpensive, but they can be sensitive to changes in the system impedance. Active filters use power electronic devices to inject harmonic currents that are equal and opposite to the harmonic currents generated by the nonlinear loads. They are more complex and expensive than passive filters, but they are more effective in mitigating harmonics and are less sensitive to changes in the system impedance. The choice of harmonic filter depends on the severity of the harmonics and the cost-effectiveness of the solution. In some cases, a combination of passive and active filters may be used. Power factor is also related to the concept of displacement power factor and true power factor. Displacement power factor is the cosine of the angle between the fundamental voltage and current waveforms. It represents the power factor due to the phase shift between the voltage and current. True power factor is the ratio of real power to apparent power, taking into account the effects of both phase shift and harmonics. In the absence of harmonics, the displacement power factor and true power factor are equal. However, in the presence of harmonics, the true power factor is always less than or equal to the displacement power factor. To accurately assess the power factor in a system with harmonics, it is necessary to measure the true power factor using a power quality analyzer. Power quality analyzers can measure the voltage and current waveforms, calculate the real power, apparent power, and reactive power, and determine the true power factor. Power factor is also an important consideration in the design of electrical equipment. Equipment with a high power factor is more efficient and requires less current to operate. This can lead to reduced cable sizes, lower voltage drops, and improved system performance. Equipment manufacturers typically specify the power factor of their product. When selecting equipment, it is important to choose equipment with a high power factor to minimize the overall energy consumption and improve the system efficiency. Power factor is also affected by the ambient temperature. As the temperature increases, the resistance of the conductors increases, leading to higher losses and a lower power factor. Therefore, it is important to ensure that electrical equipment is properly cooled to maintain a high power factor. Power factor is also an important consideration in the design of renewable energy systems. Renewable energy sources such as solar and wind power are often intermittent and may not always be available when needed. This can lead to fluctuations in the voltage and frequency of the electrical system, which can affect the power factor. To mitigate these effects, power factor correction equipment may be required in renewable energy systems. In conclusion, power factor is a complex and multifaceted topic that is essential for the efficient and reliable operation of electrical systems. By understanding the principles of power factor and implementing appropriate power factor correction techniques, industrial customers can reduce their energy consumption, lower their electricity bills, and improve the overall performance of their electrical systems. Regular monitoring and maintenance are essential to ensure that the power factor remains within the acceptable range. Working with qualified electrical engineers and consultants can help ensure that the power factor is properly managed and optimized. Remember that a good power factor benefits not only the industrial customer, but also the utility company and the environment. By reducing transmission losses and improving system efficiency, power factor correction helps conserve energy and reduce greenhouse gas emissions.